For our first video of the semester, we're going to talk about our first topic, which is talking about how two different quantities can be related to each other and how to express that. So first, we're going to show some examples of quantities that are related to one another. We're going to show how to represent these relationships between quantities. There are different ways. We can do them in tables, we can use ordered pairs, and we can use graphs. Then we're going to look at an example where we analyze the relationship between variables. One way we can do that is finding a formula between the quantities. And another is thinking about what the quantities are like to predict what the graph may look like. So here are some examples of some particular pairs of quantities that are related to each other. So for instance, if you're going out on a walk, two quantities that will be related to each other depending on how fast you go and in what direction you go are the time that elapsed at a given point and how much distance you have traveled. So depending on what time we're recording, it's been 5 seconds, it's been 10 seconds, it's been 10 minutes, you will have traveled a different distance. Filling a balloon with air, you could think of the air in two ways. You can first think of how much air is in the balloon. That could be measured in mass or weight, versus the pressure on the balloon, and that is how hard the air is pressing on the balloon. And of course, the more air you have in there, the higher the pressure. So those two quantities are related. And then you could think of like the outside temperature, like outside of a building, for instance, right? So for instance, that's going to depend on the month of the year, so what season we're in, and the average temperature. Those two things are going to be related. So different months of the year are going to give you a different average outside temperature. So there are lots of ways that these relationships can come about. One could be the value of one quantity can simply directly affect the value of the other. So for instance, in the balloon example, putting in more air directly means there's going to be more pressure because there's more air and it's going to press harder on the balloon. Outside temperature is a little bit more indirect. There you could think of it as an outside influence affecting both quantities. So there, the thing affecting what month of the year it is and the average temperature, you could think of maybe the position of the Earth in orbit. So depending on where the Earth is in orbit, you're going to be in a different month, and that's going to affect the average temperature within a given month. All right, so let's start thinking about some ways that we can record the information in a way that tells us what the relationship is between two variables. So let's think about that first example where we're talking about going for a walk, and let's suppose we begin our walk, say 3 feet away from our classroom, and then we walk away from the classroom at a rate of 4 feet per second. How can we model that? How can we represent this data to understand this relationship a little better? So the question is, what is the distance from classroom at different times? So we could just look at some specific times in the table. So we're looking at time in seconds, like 0 seconds, that's at the beginning, after 1 second, after 2 seconds, after 3 seconds, after 4 seconds. Well, by the assumptions of our problem, we're starting 3 feet away from the classroom. So at time equals 0, we have distance equal to 3. And now every time we go a second, since we're traveling at 4 feet per second, we're going to add 4 seconds. So 3 plus 4 is 7. So after 1 second, we're going to go 7 feet. Add 4 more feet to get 2 seconds, that'll be 11 feet. At 3 seconds, 4 more feet, that's 15. And at 4 seconds, 4 more feet, that gives us 19. So that gives us a way to look at the relationship between those two quantities. Now we don't have to do that in a table. We can take the same data actually and express them as ordered pairs. So instead of having like 0 and 3 in the same column, you can just say, well, it's an ordered pair of 0, 3. With the understanding that the left number is time and the right number is distance. And then time equals 1, we get 1, 7, 2, 11, 3, 15, and then finally 4, 19. The exact same data, the exact same information, the exact same relationship, just expressed in a slightly different way. Now we can also represent these ordered pairs visually using a graph. So here's what they'll look like in a graph. So the vertical one is the distance, the horizontal one is the time. And so here's what our graph is going to look like. If we have 0, 3, see that little orange dot there? That is at time equals 0, right? 0 horizontally, and vertically you go up 3. And at time equals 1, we get 7. And so we get 1 horizontally, 7 vertically. At time equals 2, we get 11. At time equals 3, we get 15. And at time equals 4, we get 19. And those are the 5 points we get. And looking at them visually in this way, we can see that the relationship between those points seem to give us a straight line, right? So we have what we will eventually recognize as a linear relationship between those two quantities. We can also express the relationship between time and distance with a formula. So we have to think about this analytically. So we're starting 3 feet away, so that's at time equals 0. And then every second we travel 4 feet. So if we just focus on the amount of distance we travel at a given period of time, if x is the time, and there are 4 feet traveled for every second, that means 4x is going to be the distance traveled. So if you put those things together, you start 3 feet away, and for every x seconds you travel 4x feet more away. That gives you a total distance from the classroom of 4x plus 3. And if you let x be the time and y be the distance from the classroom, then the relationship between those two variables is y equal 4x plus 3. So we get a formula for the relationship between time given as a variable x and distance given as a variable y. Alright, so now let's see a situation where we don't have specific numbers. Unlike the last example where we had lots of specific numbers, we knew where we were starting, we had 3 feet away initially, and we had a rate of 4 feet per second. Let's just look at two quantities, see if we can think about how those quantities work, and give ourselves an idea of what the graph might look like, at least vaguely, right? So here's the example we're going to look at. So suppose I'm in a situation where I start at a dead stop, I run as fast as I can until I can't run anymore. What does the graph of the relationship between time and distance look like in this particular example? Well, let's see. So we have to use a little bit of imagination of what happens when I'm running. First, I'm accelerating from a dead stop, so I'm not going to be going very fast. And if we think about how that's going to look on the graph, that means there's going to be a lot of time going by with not a lot of distance going along with it. So I'm going slowly, and so there's going to be a lot of time compared to not a lot of distance. As I accelerate, I'm going to go faster, which means I'm going to have shorter time, more distance, right? And so in terms of the graph, that means less horizontal movement and more vertical movement. Whereas when I'm going slowly, it's going to be lots of horizontal movement and not very much vertical movement in the graph. And then at some time, I'm going to get so tired that I'm going to have to start slowing down. I'm not going to be able to accelerate anymore. And that means, again, the graph is going to be more horizontal, less vertical because I'm slowing down. And then finally, I'm going to keep slowing down until I stop and decide I'm finished with that run. So let's see what's happening with the graph. So again, I'm accelerating from a dead stop, which means I'm going nowhere. And I'm going faster, but not very fast. So if we look at what the graph looks like, and here again, horizontal, I'm looking at time, and vertically, I'm looking at distance. What's happening is I'm not going very fast. So you can see there's a lot of horizontal distance in that graph and not a lot of vertical distance because I'm going slowly. But you notice that the graph is curving up. I'm going faster. If you look at the last part of the graph, there's a little bit more vertical change compared to the amount of time than there was at the beginning. And I'm going to keep accelerating until I get to my maximum acceleration, where again, you can now see that, if you look at that last half of the graph, not a lot of horizontal distance in terms of the time, and a lot of vertical distance in terms of the actual distance that I'm traveling. Now I'm going to begin oxygen death. That's when I stop going faster. And so I'm going to start to slow down, which means that there's going to be more horizontal distance compared to the vertical distance. So I'm going to be going slower, and that's what my graph is going to look like. You can tell I'm slowing down. The graph is stretching out horizontally more and not moving so much vertically. And then eventually I'm going to stop because I can't run forever. And so this is what my graph is look like. Now, I don't exactly know what the numbers are on this graph, but I can tell a lot about the behavior of the distance versus time just by looking at the graph, and all that behavior was based upon what I knew about the two quantities that I was looking at. So now I think you've gotten a good enough look at these to work on the activities. The title on the on Blackboard, the PDF file is called Related Quantities, and that is the one right above, the link right above this video.